last week, we said that integration is just the opposite of differentiation. So if I give you a function and say integrate f of x dx, what I'm saying is, and then you get g of x. What this means is when you differentiate g of x with respect to x, your answer will be f of x. So this is your slope over here, and then you have to work out what the curve is. With differentiation, I gave you the curve, and then you have to work out what the slope was. So we looked at a few techniques and some of the derivatives that are standard, and today we'll continue with some more examples of integrating. So these are the questions from exercise 13.2.1. We have the integral, 13.1. We have the integral of 6 dx. Now when we're integrating a constant, our function is always a straight line, because we know that on a straight line the slope is constant. So to integrate this we get just 6x plus c. Okay, and then you can always try and differentiate your 6x plus c. When you differentiate that, you get 6 plus 0, which is just equal to 6. Number 3, integral of 3x dx. To integrate this one, the exponent of x is 1, so you'll do the opposite of what you do in differentiation. So you add 1, and then instead of multiplying, you divide. So the 3 can come outside. Say this is one of the rules of integration, and this is just 3 times x to the power of 2, then you divide by 2, and because this is the indefinite integral, you add a c. So when we simplify this, we get 3 over 2 x squared plus c. And then always try differentiate what you get, see if it gives you back the original function. If it does, then you know what you did is correct. If not, you have to check your working and see if you did something wrong. And the integral of 3x to the power of 5 dx. Okay, this one we do it in the same way as the previous one. I will add 1 to 5 and then divide by 6. So this is just 3x to the power of 6 divided by 6 plus c. This can be simplified to x to the power of 6 over 2, and then plus c. 7. Integral of dx 5 x to the power of 5. Now this one here, you can look at it like this. This is the integral of 1 over 5x to the power of 5 dx. Okay, and then you can rewrite this as the integral of 1 over 5 times x to the power of minus 7 dx. Then the 1 over 5 can go outside, and then you integrate the x to the power of minus 7. So when you do that, what you have is, okay, just hold on. Okay, so when we do that, we have 1 over 5 x to the power of negative 7 plus 1, which is negative 6, and then you divide by negative 6, then plus your c. So simplifying this, you get negative 1 over 30 x to the power of 6 plus c, and then that is your answer. In number 9, we have the integral of the cube root of 2x dx. Then here we can split the cube root. So this is the integral of the cube root of 2 times the cube root of x dx. And then the cube root of 2 can go out. So this is the cube root of 2, the integral of x to the power of 1 over 3 dx. Okay, just a moment. Okay, I'm back. So here, what we do to integrate x to the power of 1 over 3, we just add 1 and then divide by that. So when we add 1 to 1 over 3, what we get is 4 over 3. So we have the cube root of 2 x to the power of 4 over 3. Then we divide by 4 over 3. Then we add our constant. Excuse me. Then we can simplify this. This is 3 times the cube root of 2 over 4 times x to the power of 4 over 3 plus c. And then this over here, you can simplify it further because cube root of 2 is 2 to the power of 1/3, and 4 is 2 to the power of 2. So what I have is this, 3 times 2 to the power of 1 over 3 over 2 to the power of 2 minus, not minus, times x to the power of 4 over 3 plus c. This is 3 times 3 over 2 to the power of 1 2/3, which is 4 over 3. and then I have x to the power of 4 over 3 plus c. Okay, so that is as far as you can simplify it. You can write the cube root and x to the power of 4 under the cube root. That is also fine. Or yeah, the cube root of 2 to the power of 16 as well. That is also fine. All right, then look at number 11. This is the integral of 3 du over 4 the square root of 11 u. Okay, so this one, again, the constants can go out. So I have 3 over 4, the square root of 11. Those can go out. And when they do, what I'm left with is the integral. I have 3 over 4 square root of 11 on the outside, and the integral of 1 over u to the power of a half du. Okay, then when I integrate this, I can rewrite this as u to the power of minus half. Then I will add 1 to half and then divide by a half. So I have 3 over 4 square root of 11 times u to the power of a half divided by a half plus c. So this is 3 over 2 square root 11 times the square root of u plus c. So that is how you would leave it. And then number 13, we have the integral of 5y to the power of 3 minus the square root of y plus 4 dy. Now we want to integrate this. This is a sum. When we integrate a sum, what we do is we can integrate each term and then add all the integrals together. So doing that, what we get is the integral of 5y cubed dy minus the integral of the square root of y dy plus the integral of 4 dy. Okay, integrating the first one, this is 5y to the power of 4 over 4 minus y to the power of half plus 1, which is 3 over 2, divided by 3 over 2, and then plus 4y plus c. Now when we integrate each of these, that one, and that one, each of them does give a constant. So you don't need to say constant here, constant there, and then another constant. This constant represents the sum of all the constants that come from each of them. So simplifying this, we just have 5y to the power of 4 over 4 minus 2y to the power of 3 over 2 divided by 3, and then plus 4y plus c, and then that is it. And then 15. The integral of 1 plus y squared over the square root of y dy. Now when we integrate this one, what we should do is we can multiply out the bracket in the numerator and then rewrite this as every single numerator over the denominator. So what we'll have is the integral of 1 plus 2y plus y squared divided by the square root of y dy So you can expand that using Pascal's triangle or by using the binomial theorem. But to the power of 2 is not a difficult expansion to make, even if you multiply it out directly. So this is the integral of 1 over the square root of y dy plus the integral of 2y over the square root of y dy plus the integral of y squared over the square root of y dy. Then you can rewrite this integral of y to the power of minus a half dy plus the integral of 2y to the power of half dy, and then plus the integral of y to the power of 3 over 2 dy, like that. Then the first one, we add 1 to the minus half and then divide by a half. So I have y to the power of half over half plus 2 y to the power of 3 over 2 divided by 3 over 2, and then I have y to the power of 5 over 2 divided by 5 over 2, and then always add your constant like that. So simplifying this, we have 2y to the power of half, or just 2 square root of y, and then we have 4 over 3 y to the power of 3 over 2, and then there's 2 over 5 y to the power of 5 over 2, and always have your constant over there. Then you are done with that integral. And some more, number 17, the integral of 1 minus x squared over the square root of x dx. So this is similar to the other one in that I will multiply out my bracket, or I'll expand it, and then I will write each of them over the square root of x. So this is the integral of 1 minus 2x plus x squared over the square root of x dx. And then we can split this. This is the integral of 1 over the square root of x dx minus the integral of 2x over the square root of x dx plus the integral of x squared over the square root of x dx. So that's what we have. Then the first one, the square root of 1 over x dx, that is the same as the integral of x to the power of minus half. So I'll add 1 to minus half, I get half, and then I divide by a half. So I have x to the power of half over a half. And then this one over here, x over square root of x, that is x to the power of half. So I'll add half plus 1, and then I get 3 over 2. So I have negative 2 x to the power of 3 over 2. Then I divide by 3 over 2. Then the last term, I have x squared, divided by square root of x. That leaves me x to the power of 3 over 2 in the numerator. So when I integrate that, I will have x to the power of 5 over 2 divided by 5 over 2, and then I must add my constant over there. Okay, now the only thing left to do is to simplify. So I have 2 square root of x minus 4 over 3 x to the power of 3 over 2, or the square root of x cubed. Let me write that. So it's the square root of x cubed, and then plus 2 over 5, the square root of x to the power of 5 plus c. So that is it. There are no like terms you can combine, so you leave it like that. In 19, we have the integral of 2x cubed dx. So with this one, it's very easy to multiply out your brackets. So this is just the integral of 8x cubed dx, because 2 times 2 times 2 is 8, x times x times x is x cubed. You integrate this, this is just 8, then x to the power of 4 divided by 4 plus c. So this can simplify, goes there once, it goes there twice, so I have 2x to the power of 4 plus c. And then you can always check, because these equations or these expressions, they're not difficult ones to differentiate, to check whether your integral is done correctly. Because with this one I can just see it's correct. The 4 will come down, multiply with the 2, I get x to the power 8x to the power of 3, and I can always write that back to that one. And then number 20, we have the integral of 2e to the power of x plus 3 sec squared x dx. Okay, so integrating this one, we'll use the sum of integrals. Then what you do is, this is 2 the integral of e to the power of x dx plus 3 the integral of sec squared x dx. Okay, so remember what we're doing when we're integrating. We say, what function do I need to differentiate in order to get e to the power of x? Now we know when we differentiate e to the power of x, we get e to the power of x. So the integral of e to the power of x is just e to the power of x. And then this 3, what function do I need to differentiate in order to get sec squared? And that is tan x. And then you add your c. And then that's it. So these are standard derivatives that you should know, be able to read from your table. Okay, then the next type of integrals, I don't know, are these fine? Do you have any questions on these ones?
No, ma'am, it's fine.
Okay, then the next type of integrals, these are those where we will use substitution. Okay, now the way these work is, these functions will look, they will be in the form, the integral of, they will be in the form f prime, in the form f prime of x, f of x dx. So what you do with these functions is you will see the derivative multiplying with dx and then the function itself. So when you see functions like that, you should know that you will have to use a substitution. So we can look at an example. If you have to integrate, for example, 2x sec squared of x squared dx. Now you'll notice this function over here, x squared, and if you compare it with that one over there, 2x is the derivative of x squared. So what you do is you'll make a substitution. You'll say let u equal to x squared. Then we know that du dx, this is equal to 2x. So what we do here is like multiply the dx. So you have du is equal to 2x dx. So now we make our substitution. Wherever I have x squared, I'm going to put u, and wherever I see 2x dx, I'm going to put du. And you can see here I have 2x dx, and that will be replaced by du. So what I have is this, the integral of sec squared u du. Notice the 2x is gone, the dx is gone, because 2x and dx make up du, and the x squared is gone, and I have replaced it with u. Okay, now the reason we make this substitution is because we know how to integrate sec squared of u. Sec squared of u is a standard integral. The integral of sec squared u is just tan of u plus c. But then we need to remember tan of u was not there in the original question. That is something that I introduced, so I unsubstitute in a way. So this is tan of x squared plus c. Then we can always check, see if our substitution is correct or the way we have done it. Now if I have tan of x squared plus c, and now I want to differentiate this, I look at this first one over here. The derivative of tan, this is sec squared, and the inside stays the same. Then I multiply this by the derivative of the inside, which is x squared. The derivative of the inside is 2x plus c. So this leaves me, sorry, not plus c, this is 0. Plus 0, because when we differentiate a constant, we get 0. So this is just 2x sec squared of x squared, right? And this is exactly what we were trying to integrate over here. Okay, so we use substitution. When you see your function, it is being multiplied by the integral, by the derivative of some part of what it is you are trying to differentiate, trying to integrate, sorry. Okay, let's look at another example. These are from exercise 13.2.1. We have the integral of 5x to the power of 4 cos of x to the power of 5 dx. Okay, so here I can already see that this function x to the power of 5, when I differentiate it, I will get 5x to the power of 4. So already this tells me this is going to be my u, and then this will be, this one here is going to be my derivative. So I make that substitution. So I say let u equal to x to the power of 5, then du, this is equal to 5x to the power of 4, and then I put dx over there. So this 5 dx is going to be replaced by just du, and then I will be left with cos of u. So the integral of cos of u du, we know how to integrate this. So the integral of cos u du, I'm just asking what function do I need to integrate in order to get, what function do I need to differentiate in order to get cos u, and that is just sine of u plus c. So when I differentiate sine of u plus c, I get cos of u, and then I put back the value of u. So this is sine, my u over here was x to the power of 5, so I have sine to the power of 5 plus c. Okay, and then again you can always try differentiate, see if you get back to that. So when you differentiate this, you get cos x to the power of 5, and then on the inside, the derivative of x to the power of 5, the 5 comes down, you have x to the power of 4, which is the original question. Then number 3, we have the integral of 6 cos 6x dx. So here again, I can see that if this is my u, the derivative of u will be equal to 6. So that substitution will work. So we let u equal to 6x, then du is equal to 6 dx. So I will replace the 6 and the dx with just du, and the 6x I'll replace it with u and then integrate. So this is the integral of cos of u du. Then the integral of cos of u, just like in the previous one, this is just sine of u plus c. Then remember that u is 6x, and then that is my final answer. So again, you can always very quickly check that the derivative of this function here is what you are asked to integrate. Then number 5, the integral of cos of 9x dx. So this one is a little bit different, but our approach will be the same. This time I will let 9x equal to u. So I will say u is equal to 9x. And then I will differentiate du. This is equal to 9 dx. But if you look at what we have over here, there is no 9. So what I will do instead is I'll divide by 9 on both sides. So I have 1 over 9 du is equal to dx. Then this dx, I will replace it with 1 over 9 du. And then this 9x over here, I will replace it with the u. So what I have is cos of u times 1 over 9 du. Now we know that when we have a constant multiplying a function and we're integrating, we can always take the constant out. So I have 1 over 9, the integral of cos of u du. And again, this is just 1 over 9 sine of u plus c. U is 9x, so I have 1 over 9 sine 9x plus c. Then again, try and differentiate this function that you've got. Make sure it is the correct answer. In doing that, you differentiate sine, you get cos 9x. Differentiate 9x, you get 9. The 9 will multiply with the 1 over 9. Those will cancel out, and you'll just be left with cos 9x. The derivative of c is equal to 0. And then these are question 2, number 1. We have to integrate 3x squared sec squared x cubed dx. So here you can see x cubed, the derivative is over there. So this is an easy substitution. You let u equal to x to the power of 3. This means that du is equal to 3x squared. Okay, and then we make, dx here, it should be a dx, very important. So you will make this substitution. You can see the 3x dx, this is just du. So I have the integral of sec squared. Instead of x cubed, I put u, and then I put du instead of what I have over there. So then the integral of sec squared u du, this is just tan of u plus c. So this is tan of u plus c, and u is x to the power of 3 plus c. Then 3 of question 2. We have the integral of 2x squared sec squared x to the power of 3. So this is similar to the one we just did. Okay, the only difference is the coefficient over there, but we would do it in pretty much the same way. So we let this equal to u, so let u equal to x to the power of 3. This means that du is equal to 3x squared dx. But what I have over here, I have a 2. So what I can do is I can multiply both sides by 2 over 3. So if I have 2 over 3 du, this is equal to 2x squared dx. So now I have the 2x squared dx, which is what I have there, and I will replace it with du. So my integral becomes sec squared of u times 2 over 3 du. Then the 2 over 3 can come outside the integral. This is sec squared u du. And the integral of sec squared, that is just tan. So I have 2 over 3 tan of u plus c. This is 2 over 3 tan, and then instead of u, I put x to the power of 3 plus c. Number 5, integral of sec squared 6x dx. Okay, so again, similar, and let u equal to 6x du. This is equal to 6 dx. But over here, I don't have a 6 dx, I only have dx. So I'll divide both sides by 6. So I have 1 over 6 du. This is equal to dx. And then now I'm ready to make my substitution. This is the integral of sec squared u multiplied by 1 over 6 du. So this is 1 over 6, the integral of sec squared u du, which is 1 over 6 tan of u plus c. This is 1 over 6 tan of 6x plus c. Then number 3, the first one, we have the integral of 2x x squared plus 5 to the power of 10 dx. Okay, so here I look at this, I have x squared plus 10. The derivative of x squared plus 10 is just equal to 2x. So I can let u equal to x squared plus 5. This means that du is equal to 2x dx. Then I can make my substitution. So this will be the integral of u to the power of 10. So this becomes my u, and then 2x dx, that is equal to du. So this is u to the power of 11 over 11 plus c. And then substitute u back. So you have x to the power of 2 plus 5 to the power of 11 over 11 plus c. So again, try and differentiate this, see if you get the original question back. The 11 will come down, you'll multiply with that one, they cancel out. I'll be left with 10 at the top, and then multiply by the derivative of the inside, which is 2x. And then the derivative of the constant is just 0. And then number 3, we have the integral of 2x plus 2. We have x squared plus 2x minus 3 to the power of 7. This is with respect to x. Now integrating this one, if I look at my bigger bracket and I differentiate that, I will have 2x plus 2, which is exactly equal to this one. So I can let u equal to x squared plus 2x minus 3. This means that du is equal to 2x plus 2 dx. This is in brackets. So making the substitution, I have the integral of u to the power of 7, and this is du. So this 2x plus 2 and the dx makes up du. So integrating this, I have u to the power of 8 over 8 plus c. Then unsubstitute u. This is x squared plus 2x minus 3 to the power of 8 over 8 plus c. Number 5. Then the integral of sine the power of 5 of theta cos theta d theta. So looking at this, I can let u equal to sine theta. This means that du is equal to cos theta d theta. So I already have the cos theta d theta over there. That will just become du. So my integral is actually just u to the power of 5 multiplied by du. Okay, then I integrate this. This is u to the power of 6 over 6 plus c. Then u is sine theta, so I have sine power of 6 of theta over 6 plus c. Can integrate e to the power of cot x and cosec squared x dx. So again, here we make a substitution. We let u equal to cot x, then du, this is negative cosec squared x dx. So I can see I will substitute that one over there. And then when I look at it, it's positive. So here I have negative, so I need to divide by negative 1 on both sides. So this means that negative du, this is equal to cosec squared x dx. So now this cosec squared x dx over there, I will just replace it with negative du. So what I am actually integrating is just e to the power of u times negative du. And doing that, I have negative integral of e to the power of u du. And when we integrate e to the power of u with respect to u, it doesn't change. This is just e to the power of u plus c. And this is negative e to the power of cot x plus C. Okay. And look at another one. These are now the questions in exercise 13.2.2. There's 1 square root of x minus cos x dx. Okay, this is a pretty straightforward integration, because you just integrate this one and that one, and then you work out the difference. So this is x to the power of 3 over 2 over 3 over 2 minus the integral of cos x is sine x. This is sine x, and then you add a constant. So this is 2 over 3 x to the power of 3 over 2 minus sine x plus c. Then number 3, we have the integral of x squared plus 1 to the power of 4 dx. So again, this will be my u. So I let u equal to x squared plus 1. This means that du is equal to 2x dx, but over here I only have x dx. So what I do is I'll divide by 2 on both sides, divide by 2, divide by 2, then I have half du is equal to x dx. So my integral just becomes u to the power of 4 times half du. And then the half can come outside, so I have half the integral of u to the power of 4 du, which is just half u to the power of 5 over 5 plus c. Okay, this is u to the power of 5 over 10 plus c, which is equal to x squared plus 1 to the power of 5 over 10 plus c. Okay, I think we can do one more. The integral of x squared e to the power of x to the power of 3 dx. So here I see that if I differentiate x to the power of 3, I will end up with 3x squared. So that will be its derivative. So I let u equal to x to the power of 3, means that du is 3x squared dx. Then divide by 3 on both sides. This means I have 1 over 3 du. This is equal to x squared dx. So now I can substitute this x squared dx with 1 over 3 du. So what I have is e to the power of u times 1 over 3 du. Okay, so the 1 over 3 can go out. This is the integral of e to the power of u du, which is 1 over 3 e to the power of u, because when we integrate e to the power of u, it doesn't change. Then you add c. And this is 1 over 3 e to the power of u. U is equal to x to the power of 3. And then c. Right, so that is how you would integrate by using substitution. All you have to do is look at what you have. Somewhere you will have the derivative of another function. Should be able to recognize that. The difference may be with a constant, like we did with this one. the difference between the derivative of x cubed and x squared was just a constant 3, and when the difference is a constant you can always divide or multiply both sides by that. Okay, so there are more questions in the book. I put it on the group. I did the odd numbered questions. You can always try the even numbered questions, and they are pretty much the same, nothing too complicated. Do you have any questions?
No, ma'am.
Okay, so if not, then we'll continue tomorrow. Tomorrow the class is at 9:30. Okay, have a good day.
Thank you, ma'am.